Hey guys, welcome back. Today let's solve the problem, check completeness of a binary tree. So we're given the root of a binary tree and our task is to determine if it is a complete binary tree. Now by definition, a binary tree is considered complete if every single level of that binary tree from the root is complete except for the last level in that binary tree, which must be complete from the left going to the right. As you can see from the example that's given, the last level of this binary tree is complete from the left and it is missing only one single value at the last level. It's pretty simple to note that once we have a binary tree, we can easily check to see if the last level is complete. You can clearly see that from this example, from the left to the right, all the values on the left side of this tree are filled and only the last value is missing to the right side of the tree. However, if any value was missing to the left of this tree, say the first value, this tree will not be considered complete. It's the same case if any value was missing in between, like this 5 or this 6, but this last value was existing. This tree will not be considered complete. How would we check that using an algorithm? Now, you might know that for any binary tree, the two most common algorithms are depth first search and breadth first search. In this case, the algorithm that can help us traverse this tree level by level, each layer by layer, is the breadth first search, which we are going to use. How can we implement this? In our algorithm, we will be using the queue data structure to implement our breadth first search so that we can traverse this tree layer by layer. The first layer will be the root node, and once we add the root node, we'll proceed to adding the left and the right children of this node to the queue data structure. We'll continue with this algorithm until we add the last children in this layer. So you can see from this side, we will add the next two nodes, the left and the right node. We'll also add this left node from this position. However, once we add the 6, we will also add the next value, which will be a null. What you will notice in this algorithm is that for a tree that is considered complete, once we add a null, we expect that all the other values that come after this will also be null. Assuming that we also add the next two nodes in this tree, so we'll be adding this as nulls. These do not exist. We'll also come here and add the two nodes which do not exist as null. The same is true for this. So the last layer of this tree will actually be represented by these nulls, which will be added into our queue. And once we find a null in our algorithm, we will assume that all the remaining values must be equal to null. That is how we'll identify if this binary tree is complete or not. Let's take an example. If this tree had two other nodes that represent the last or the final layer, but we identified a null value in this previous layer, if our algorithm ever finds that this next layer is not complete with nulls, then we know that this tree is not balanced. It is not complete. However, if this node was not a null and it contained a value, then this tree would be considered complete because the leftmost side is complete and the rightmost side is what is null. The time complexity for this approach will be an O of n. We're just doing a normal BFS, and the space complexity will just be a big O of n as well. That said, we can check out the code. Just like we discussed, we'll be using a queue data structure to hold all the values that we are traversing, and we will initialize this queue with our root value. Our algorithm will be running while the queue is not empty. And we will be popping from this queue to the left side and adding to it from the right side. So we can pop a node and just say queue.pop left. Once we pop a node, we need to check, is this node empty? Is this node null? If it isn't, we'll just take the queue and append the node's left and right children. So we can just append the left child, and we can take the queue.append the right child. Otherwise, this is the interesting part. Because we found that this node is indeed null, we want to make sure that all the other values after this value must also be null. So you can write a nested while loop again. While the queue is not empty, we will check if the value that we pop is not null, then we immediately return false because we've identified that we have found a value that is not null, and we are expecting that this queue only has null values after this initial test. If we don't return at this point, it means that all the values that were remaining in our queue are null, and we will exit out of this while loop. When we go back, we will exit again because now the queue is empty, and so it means that all the values that were remaining were null, and we've just found a complete binary tree, so we can return true outside here. Let's run the code and see if it works. And as you can see, it works and it's pretty efficient. If you enjoyed this section, please like and subscribe for more content just like this, and I'll see you in the next one.